Hi, this is Adam Griffin, and this is the first video for this week. I'm going to be doing problem 49, and the problem is in an old-fashioned amusement park ride, passengers stand inside a 5-meter diameter hollow steel cylinder with their backs against the wall. The cylinder begins to rotate about a vertical axis, and then the floor on which the passengers are standing suddenly drops away. If all goes well, the passengers will stick to the wall and not slide, and then it gives the static coefficients of friction for clothes against steel, which is 0.6 to 1, and the kinetic coefficient, which is between 0.4 and 0.7. So there's a sign next to the entrance that says no children under 30 kilograms allowed, and we have to find the minimum angular speed in revolutions per minute for which the ride is safe. So we will take all of our variables out of here just so we can visualize them. So we have our radius, which is 5 meters, our mass, which is 30 kilograms, and our range for our coefficient of static friction, which is between 0.6 and 1. But because it wants us to find the minimum angular speed for which the ride is safe, we should assume that there is a person in there with very slippery clothes. So we're going to use this one because that'll make sure that everything is ready. So we have our diagram right here. This is like a top view. So we have our center and then our radius to the wall. And then we have a person right here who weighs 30 kilograms, which is worst case scenario. Because again, we want to find the minimum safety threshold. So we have our 30 kilogram person right here, right on the edge, and they have their angular velocity right there. So from the equations of circular motion in the textbook, we see that this right here represents, here I'll grab this cursor so you can see better. This represents the force in the radial force. So that points like outwards because we're trying to move along this line, but because there's a wall there, we're getting curved around. So the acceleration is pointing inwards, but we feel a force pointing outwards. So we can find this, which is also equivalent to Fs. So it's mass times velocity squared over our radius. So we can plug that in, and that will be Fs for later equations. So Fs, we can set equal to Fs max to find the force of the static friction. So we have our coefficient, which is right here, 0.6 times mass times gravity. We can plug all of that in, and we find that Fs max equals 176.4 newtons. So using that, we have our equation up here still. We can rearrange that and solve for velocity. So once we do that, we find that velocity equals the square root of our radius times Fs max over our mass. So once we do that, we can plug in all of these variables, and we get 5.42 meters per second for our angular velocity. But that's in meters per second, and it wants it in RPM. So this right here is going to stand for our like speed of rotation. So we can solve for that for radians per second with our speed divided by our radius. So we have 5.42 meters per second divided by 5 meters equals 1.08 radians per second. And then we can convert that into RPM by multiplying it by these conversion factors. So this one tells us how many radians are in one like revolution. And then this one converts it from seconds to minutes. So once we plug all of that in, we find that our speed, our minimum speed, is 10.356 RPM to have a safe ride for a little tiny child with super slippery clothes. So that is the answer to 49, and thank you.